So the new model of the atom is our quantum theory. We know electrons don't actually circle the nucleus. Instead, they're contained in 3D regions of space. So the quantum theory is going to explain the space that they take up. And it's based on some history. Heisenberg's uncertainty principle says that you can't know the location and the speed of an electron at the same time. So electrons move very, very quickly, so we can't know how fast they're moving and exactly where they're located at the same time. So we do have some uncertainty here. Schrödinger had a wave equation, and what it really said was that electrons can act like a wave. So they give off wavelengths and they give off frequency. De Broglie looked at the electron as a particle. So this would give us our wave-particle duality. So the electron can act like two things, a wave and a particle. Now, based on those ideas, we came up with quantum numbers. Quantum numbers tell us the energy level, the sublevel, the orbital, and the spin of the electron. So it's like an address to the electron. Where is the electron exactly located? The first quantum number is your principal quantum number. It's represented by the letter N, and it tells us the main energy level. So N represents the energy level. So if N is equal to 1, then you're on the first energy level. If N is equal to 7, then you're on the 7th energy level. As the levels increase, the amount of energy that electron has also increases, so it's a direct proportion. So an electron sitting on the 7th energy level has much more energy than the electron sitting on the first. To know how many electrons can go in each energy level, we use 2n squared. So if we want to know how many electrons are on the 7th energy level, we would say 7 squared times 2 would give us 98 electrons allowed in the 7th energy level. The second quantum number is for the sublevel. It's symbolized by a lowercase l. Sometimes you're going to see it written as a lowercase cursive l. It tells us the shape of the sublevel. Each sublevel is assigned a letter, so you have S, P, D, F. So there's 4 sublevels that you have to know, and they're called S, P, D, and F. Now the S sublevel is shaped like a sphere. The P sublevel is shaped like a peanut. So it has 2 lobes. The third sublevel is a double peanut. So you have the 2 lobes of one peanut, and then it's on top of another 2 lobes. And then you have the flower for F. Now you don't really need to know too much about F, except for that it's in the shape of the flower and the number of orbitals. Each sublevel increases with energy. So S has the least amount of energy, and the flower, or F, has the most energy. The number of the energy level tells you how many sublevels are contained in that energy level. So if we're on the first energy level, then we have 1 sublevel, and that's the S. If we're on the second energy level, we have 2 sublevels, S and P. If we're on the third energy level, we have 3 sublevels, S, P, and D. If we're on the fourth energy level, we have 4, S, P, D, and F. If we're on the 5th energy level, we have 5. The first 4 are S, P, D, F, and then we have a 5th one that we don't really need to know about, but it is there. The third quantum number tells us how many orbitals each sublevel contains. In other words, how many different ways can we look at that shape on a 3D axis? Well, a sphere only has one way of viewing it on a 3D axis. It doesn't matter if you rotate it, it's going to look the same. So the S sublevel has 1 orbital. The p sublevel, the peanut, you can actually rotate it 3 different ways and get a different view. So the p sublevel has 3 orbitals. The d sublevel, that double peanut, you can actually rotate 5 ways, and the f is 7. So it's your odd numbers, 1, 3, 5, 7. When you have more than one orbital possible, they're called degenerate. So even though the p has 3 orbitals, all of 3 of those orbitals have the same amount of energy. The d has 5 orbitals, but within those 5 orbitals, they're all the same amount of energy. Same with the 7 of the f. The 4th quantum number is your spin. So each orbital can hold 2 electrons, as long as they have different spins. And we're going to show that they have different spins by using an up arrow and a down arrow. So each arrow is an electron, and the different spins would be up and down. Electron configuration is based on 3 rules. Your Aufbau principle, which states lowest energy first. So the electrons fill from the energy level closest to the nucleus and then build out. So the first energy level has 1 sublevel, S. The second energy level has 2 sublevels, the S and the P. The third energy level has 3 sublevels, S, P, and D. The fourth energy level has 4 sublevels, S, P, D, and F. The fifth has 5, S, P, D, F, and then one that I don't need to know. 6 has 6, S, P, D, F, and 2 more that I don't need to know. And then 7 has 7, S, P, D, F, and then 3 more that I don't need to know. Now, it would be nice if we could just read Aufbau's principle from left to right, but that's not actually how it's done. It's read on the diagonal. So the first electron's going to fill the 1s. Once 1s is filled, we'll go to 2s, then 2p, then 3s, 3p, and then we'll fill 4s, and then we'll go back and pick up the 3d. So there's a little bit of a change here. So we're not reading from left to right, we're reading on the diagonals, so you have to be careful. After 3p is 4s, then 3d, then 4p, then 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, and so on and so forth. So you have to read this on the diagonal. Now this diagram is not given to you on the test, so you'll have to remember it, and I'll give you another option of remembering the order in our next lesson. So Hund's rule says that if you have more than one orbital, the electrons fill one at a time before they pair. So that's like getting onto a city bus with a bunch of strangers. You're not going to want to sit next to the stranger, you're going to want to sit in the empty seat. Once all the seats are filled, then people start sitting together. Electrons do the same thing. If there's an empty orbital in that sublevel, they'll fill the empty orbital first, then they'll go back and pair. Pauli exclusion principle states that only 2 electrons can go in an orbital, and they have to have opposite spins to have the lowest energy. Okay, so we're going to do some orbital notation. Orbital notation uses lines and arrows. Now, the line represents the orbital, and an arrow represents an electron. So if we pick carbon has 6 protons, so it has 6 electrons when it's neutral. Well, based on our Aufbau's principle, we're going to fill 1s first because that's the lowest energy. The s sublevel has 1 orbital, and in that orbital I can hold 2 electrons based on the Pauli exclusion principle. So I have 2 arrows, 2 electrons, I need 6. So after the 1s, we'd read the next diagonal, 2s. the s sublevel has one orbital. It doesn't matter what energy level you're on, the s sublevel has one orbital. Each orbital can hold 2 electrons. So now I'm up to 4 electrons and I need 6. So after that we fill the 2s, we're going to fill 2p. Well, the p sublevel has 3 orbitals. Now I only have 2 electrons left to put in there. Hund's rule says they're going to want to go to their own orbital before they pair up. Because these orbitals are degenerate, it doesn't matter which 2 orbitals you put electrons in, as long as the electron is going the same direction. So Hund's rule says one at a time before you pair up. That's why our electrons are separate. And because these orbitals are degenerate, it doesn't matter which one we put it on. So you have to draw the blank orbital because the electron could have been placed there. So all options have to be shown. If we do magnesium, magnesium has 12 protons, so it has 12 electrons. So we'll start at the lowest energy, 1s. That's 2 electrons. The next energy level is 2s, again 2 electrons. The next energy level is the 2p. Every p sublevel has 3 orbitals. I'm at 4 electrons and I'm trying to get to 12. So 4, 5, 6, 7 by themselves before they pair up. 8, 9, 10. So I still have 2 more electrons. After you fill the 2p, you're going to fill the 3s. Each s sublevel has 1 orbital, and I can place my remaining 2 electrons on that orbital as long as they have opposite spins. Alright, if we look at titanium, titanium has 22 protons, so it has 22 electrons. The lowest energy level is 1s. Each s sublevel has 1 orbital and can hold 2 electrons. After we fill the 1s, we would go to 2s. Each s sublevel has 1 orbital and can hold 2 electrons. After the 2s, we would have 2p. Each p sublevel has 3 orbitals. We would fill one at a time before we pair up, and we have plenty of electrons because we're only up to 10. After we fill the 2p, we would fill 3s. The s sublevel has 1 orbital, and we can put in 2 electrons. So now we're up to 12. Well, Hund's rule says Aufbau's principle says after we fill the 3s, we're going to fill the 3p. And each p sublevel has 3 orbitals, one at a time before we pair up. And we're up to 18 electrons. And we're trying to get to 22, so we still need to go a couple more. Whoops. So after the 3p, reading the diagonal, we're now going to fill the 4s. Well, each s sublevel has 1 orbital, so I can put 2 electrons there. So now I'm up to 20 electrons, and I have 2 electrons left. So after the 4s, we go back up and pick up the 3d. Well, the d sublevel has 5 orbitals. I only have 2 electrons left, and Hund's rule says they're going to want to go into separate orbitals before they pair up. So they're going to be by themselves in a seat. They have to be going the same direction, but it doesn't matter if they're both pointed up or both pointed down. And it doesn't matter which 5 of the orbitals you choose. So we could put 1 electron there and 1 electron there if we wanted. They're by themselves, going the same direction. That's lowest energy.